Hi everyone, and welcome to Lab 10. I'm ready to go ahead and finish up this lab, and we're going to go ahead and build a stopwatch. We're going to use the information that we've learned in class on RTL, register transfer logic, and we're going to follow through the process of designing a processor using HLSMs. And so we need to basically build a stopwatch that's going to count up to a specific value. If we take a look at our notes about the stopwatch, there are several tasks. The first thing it should do is it should display the time as an 8-bit binary number on our LEDs. So we'll actually see the LEDs counting up in binary. We're going to start at 0. There are two inputs, S and R, and we have 3 states. From the stop state, we're going to press S, which causes the timer to begin. And once the timer is counting, we press S again to stop it. Okay. We take a look at the standard architecture for a processor. We see that we have a controller along with data path. Okay. Looking at the process in a little bit more depth, we have our process steps. We know the first thing we have to do is capture an HLSM. Okay. And so that's actually given to us in the lab. Here's our HLSM, okay, and we also see that on the lab page. Looking at the lab page, we see that we have our HLSM, okay. Going back to our notes, we have some information here. We know that there are 2 inputs, S and R, okay. S allows us to continue to count, okay. Here it goes from stop to run if S is high and R is low. And then if we're counting, then if we press S again, it goes back to stop where we're not counting. Okay. And so that is our HLSM. Remember that with HLSMs, unlike FSMs, we have multi-bit outputs. We see our multi-bit output called T-reg. We know that multi-bit outputs must be registered, and so we're calling our output T and our registered output T-reg. We see that our register is initialized when we're in the initialization state, S-init, and then when we're in S-run, this T-reg is assigned to T-reg plus 1. So here we are counting. Looking at the next step in our process, the first thing we have to do is to create a data path. So to create a data path, we have to look at our components in our library. We know that there must be a registered output. We said that multi-bit outputs must be registered. So we have this idea that there must be a register output. And we see that it is 8 bits wide. That is given to us in our project description. Going back to our project description, we see that it's 8 bits wide. Right? And so we know T-reg is 8 bits wide. Continuing on with some notes about our data path, we want to go ahead and take a look. These are the tools that are in our library. These are the tools that we have gone over in class. Since we are counting and since we have to register, a good suggestion is to use the counter. We know that the counter does allow us to increment by 1, and it also is registered. So this handles both our register and our incrementer. So we can use a counter. Okay, and as a matter of fact, the lab tells us which counter to use. If we go over to our lab page, we see that the counter that we're supposed to use is our HLSM. Here, from our HLSM, the counter that we're supposed to use is here, our LPM counter. Okay, so we have to use the LPM counter. And so that's the one that we'll choose. And if we take a look at the LPM counter, we have several things that we want to do. So here is our LPM counter, and we see that we have inputs of S clear, and we also have count enable. Okay, we're going to find this counter in our symbols in our toolbox for Quartus 2. Just a couple other thoughts about that. We're going to notice, and we saw that up here, that there are several other inputs that we need to handle. And so again, we're going to use the clear, the S clear, to handle this initialization from our HLSM, and we're going to use count enable to do the incrementing. When count enable is equal to 1, then we can increment. This counter is actually the only counter that's available from Quartus using schematic capture, and it has a lot more functionality that we need, so we do have to address each of those other inputs. Now, if we continue on, we're going to create a data path, and so I think our manual tells us what we need to do is basically we need to create that data path. If we go over to Quartus, we're going to start a project. Our project is going to be called Stopwatch, just like we've started other projects, so we know how to set up a new project. And then we want to create a data path. If we take a look at our data path, we can open up a new BDF. Just go into your schematic files and choose a new BDF for new. And once we've done that, we can actually call it data path. And so this is the one that we're setting up. And we see that we have our LPM counter. You can find that under symbols, under the Quartus libraries, under mega functions, and under arithmetic. So if you scroll down, you can find the LPM counter right here. And so this is basically what it looks like, and a couple things that we have to do. We have to set our parameters. The only parameter we're going to choose to use these other inputs instead, but you do have to set the width, so you can just click on the parameter and set the properties to be 8 bits wide, okay? And so once you've done that, then you should see it showing up here. You've added the counter to your BDF. Go ahead and ground a lot of the inputs. Notice we can ground our asynchronous inputs, asynchronous clear, asynchronous load, and asynchronous set. Notice that I pulled up the symbol for ground. Again, you know how to find that. Going up to symbols, going to the libraries, going to primitives, and going to other to find ground. And there's our ground. Likewise, when we need VCC, the same thing here. Okay, and so we have that to give us our logic 1 and our logic 0 inputs. And so go ahead and ground your asynchronous inputs. We want to tie carry in high because we're going to add 1, and we want to tie clock enable into 1. As I said, this counter is registered, and so we're going to use a clock input for this counter. Okay, we have our S clear, our synchronous clear, and that is the clear that we want to use for clear. We don't want to use asynchronous clear. We want to use synchronous clear. So go ahead and give an output for S clear, and then excuse me, I have actually set up an external load. This is a synchronous load, just to show you what you could do. I put some data on there. This was just arbitrary. I put 8 bits ground, and I just happened to choose 1 bit as VCC, just to show the differences if I loaded the data. I did find with this counter that you do have to have some data on that data bus just to make it work. So go ahead and give an output for S load. Go ahead and set 8 bits of data. And notice I called them ground and VCC. You can make them all ground, you can make them all VCC, whatever you prefer. We're not actually going to ever use that, but go ahead and put those on there. And then also synchronous set, we're not going to ever set it high, so I just grounded that as well. I have my 8-bit outputs. This is my registered output that's going to come out of the data path. Again, the counter has registers in it, and so that is 8 bits wide. So that is my data path component that I need for this HLSM. Okay. And so going back to our thoughts about what we need to do next, we have created our data path. We can go ahead and save that as data path in Quartus 2. And then the next thing we need to do, we see that the next step in our RTL design process is to connect the data path to a controller. Just looking at some thoughts about that, we know our controller is what we learned in Chapter 3. We know our controller is made up of a of a state register along with combinational logic. And we see that the outputs of our controller are going to be the control lines for our data path, our clear and increment. Okay, our inputs into our controller are going to be our external inputs S and R, and then we also need clock. Okay, here's the general model for that processor made up of a controller and data path components. Okay, and so moving down for some thoughts, we want to go ahead and go back to Quartus and connect our data path to a controller. So going back to Quartus, we have our data path, and then we need to basically, we can create a stopwatch. And notice here I have my data path that I have created a symbol for from my datapath.bdf. And then I also have a symbol for FSM. So we have to create this finite state machine, which is our controller. We can go ahead and open up a BDF called FSM. And notice it's made up of state registers and combinational blocks, just as we would expect. Okay. Now, how do we get from this idea of an FSM here to the next step? Okay. So the next step, we have, if we created the BDF called stopwatch, and put our data path in it, we know that this FSM is what we need to control, we need to build. And so we're going there, and the steps for that are basically to derive the controller's FSM. So how do we do that? We know the FSM is going to have those outputs of clear and increment. Notice now, I want to go back to what we called our HLSM. We no longer have T-reg is assigned 0 and T-reg is assigned T-reg plus 1. We have changed those to what the names of the outputs are, clear and increment, which are indeed the inputs into our data path, clear and increment. Okay, and so now we know, and notice these are 1 bit because this is now a finite state machine rather than a high-level state machine. Each of these are 1 bit wide, and we can write clear is equal to 1 in the init state, and increment is equal to 1 in the srun state. Okay, and so the next thing we do, just like we did in chapter 3, is decide how big our state register should be. Taking a look at our, we could call our finite state machine now. We see that we have 3 states, right? And so we're going to basically set up that controller. We can set up a state table listing all of the names of the states and each of the transitions. And so we can also go ahead and encode. If we encode with 2 bits, if we encode in binary, then we know we're going to use 2 bits to represent 3 states. And so we have this idea of a state register. Going back to our Quartus, I have created a BDF called state register. Going there, notice it's made up of 2 D flip-flops. Okay, I have my next states as my inputs, next state 0, next state 1. I have my outputs of state 0 and state 1. I have also used the asynchronous resets here, reset N, just in case your machine gets stuck and you need to reset. This allows you to have your key 4, we're going to use key 4 to handle this asynchronous reset. Now this is different than the resets that we're using to clear in state 0 in our init state. So just be aware of that. This is a different clear. Okay, this is an asynchronous clear. All right, so that is the BDF for state register. You need to create that using binary. We have 2 flip-flops. And so then we go to the combinational logic, just like we did in chapter 3. We know that we're going to write combinational logic equations. We have finish out your state table for your finite state machine, listing the transitions, right? So we have our transitions listed in our table. We have them encoded. We have equations for our next state. We have equations for our outputs, clear and increment. Then we can go ahead and we can open up our combinational logic block, right? That's given to you. Add that to your project. Write your equations into your combinational logic block. Initially, they're set at 0. Go ahead and write the SOP equations for those from your state table. Add that to your project. And then in your FSM, you have the symbol for your combinational block. You have your symbol for your state register. You have your connections between them, your inputs going into your combinational block being the states, your outputs out of the state register being the states, and likewise your outputs out of the combinational block are next state, which are then fed back into the state register as inputs. And so we have our FSM, and we can create a symbol for that, and we've created a symbol for our data path, and so we can put both of those together into our stopwatch. This is the file this is the level that you're going to want to test on. Notice our test files are called stopwatch test and stopwatch test do. Just taking a look at those, make certain that you have all of the names listed as stopwatch. You should not have to change anything here. Here are the names that I used for my input ports and my output ports. You should have all of those. Notice S load is capitalized. Not sure why I did that, but just be aware. So when you're looking at the stopwatch, try to follow the same patterns that I use. Lowercase for S and R, clock, and my asynchronous input reset N. And then I have uppercase for S load, and also uppercase for my output T, right? T 7 through 0, lowercase. And I put increment in here as an output. This is the output out of your FSM. Create an output called inc. That it is looking for that in your stopwatch test.vt. So just be aware of that. Okay. All right. And so, and the reason I put that in there was because students sometimes don't actually have it incrementing. I also have an output for the states so that you can keep track of what state you're in, right? Because you want to make sure that it's changing states. So that's a great way to debug. When you're debugging, check your states first. You know how to zoom into Model Sim and check where the first error is. Go back to the time clock right before that and see if you're in the state that you expect. You know that you can come here and when you're looking at each of the tests, you know, you can check the test names. The first character is usually not displayed, so if it just happens to say R press from run stop, you know that it's actually this SR press from run stop. There are only a few tests. I think there's less than 25, so you shouldn't have any problem debugging. All right, and so once you have your stopwatch working properly and you've passed all the tests, obviously I did not test every single case, but that should get you through making the stopwatch work. And then you want to go ahead and use the stopwatch top PDF that I have attached. Let me just fit this into the window, and we see that I have added an additional counter, right? This is a clock divider. I'm not sure if you can see the whole thing. I think you can see this part of it. You might not be able to see how wide it is. This is 24 bits wide. This is all given to you. And if we take a look at zooming in the top level, that we can actually look to see that we are basically using here for our stopwatch, we're using pin 18. Okay, pin 18, the output of those 24 bits that are coming out of the clock divider, I'm using bit 18. Okay, if you've gone ahead and made your Excel spreadsheet and you figured out each of the divisions of 50 megahertz to find out what the period is, you can figure out what the frequency and period is of this particular circuit. Okay, and so that takes you through, and oh, I'm sorry, as far as what inputs and outputs, we have that the push button keys, key 3 is S and key 2 is R, right? So we have key 3 is S and key 2 is R. I had to add some more pipelining. I have a one shot here, and I have an additional pipelined D flip-flop just to try to reduce the bouncing. We've talked about before that sometimes at faster clock rates, one D flip-flop in series is not enough to slow it down. And so here I've added a second D flip-flop. I've also added a little one-shot circuit. I gave you each of those. I gave you the one-shot. You'll have to create a symbol for that. And I've given you the button debouncer. You'll have to create a symbol for that using that in this top level. And so, but you should not have to make any changes to this. Make certain that you have the top level QSF that was downloaded. This has the pin assignments. I also have in here the pin assignments for SSG, all of the outputs of your clock divider. I've changed the name, and I don't have on here an actual port called clock divider. If you want to go ahead and see each of these bits, if you want to see each of these bits, you can just have an output, and I happen to call them SSG. And so then that would show you each of the 24 bits. You could see that they were divided by 2. As I mentioned in class, you cannot see the transitions changing very quickly. It's not until you get to about 16, to bit 16, that you can actually see a transition. Okay, and so once you have that, you can go ahead and just make certain to turn off when you're running this top. Go into settings and turn off in the simulation. You do not want to run the simulation for the top level. Set your native link settings to none. Right? If you go back and you make changes and you want to run it again, you'll have to go back, click it on. You'll have to set this to stopwatch test. You'll have to make certain that your test bench has your stopwatch test.vt as the associated test bench files, and you'll also have to use your .do file in order to make model sim work, right? Which it should find your stopwatch test.do. Again, you'll need these if you're running model sim. When you're using the top level, you do not run model sim. Okay, and so that takes you through tasks 1 and 2 of the lab. And I'll stop this video and we'll start up a new one for the rest of the lab.